Today we are going to explore the fascinating story of how humans learned to measure temperature, one of the most important physical quantities in nature. Temperature is a measure of how hot or cold something is, but how do we quantify it? How do we compare the temperature of different objects or substances? And how do we agree on a common scale or unit for temperature? The history of temperature measurement goes back to ancient times, when people used their senses of touch and sight to estimate how hot or cold something was. For example, they could feel if water was warm or cold, or see if metal was glowing red or white. But these methods were not very precise or reliable, and they depended on subjective judgments. They also did not allow for accurate comparisons or calculations involving temperature. The first attempts to create a more objective and standardized way of measuring temperature were made by some Greek and Roman philosophers and physicians. They used devices called thermoscopes, which were tubes filled with liquids without scales marked on them. The liquids would expand or contract when heated or cooled, indicating a relative change in temperature. One of the earliest thermoscopes was invented by Philo of Byzantium in the 2nd century AD. He attached a hollow lead sphere to a U-shaped tube and placed the free end of the tube under water. When he exposed the sphere to sunlight, bubbles would form in the water as the air inside the sphere expanded. Another famous thermoscope was designed by Hero of Alexandria, who used a glass bulb with a long neck that dipped into a container of water. When he heated the bulb with fire, some of the water would be pushed out of the container by the expanding air. When he cooled the bulb, some of the water would be sucked back into the container by the contracting air. These thermoscopes were useful for demonstrating the effects of heat and cold on air and liquids, but they had some major drawbacks. They did not have any numerical scales or units to measure temperature. They were also affected by changes in atmospheric pressure and humidity, which could alter the volume of the air or liquid inside them. The next breakthrough in temperature measurement came in the 17th century, when some Italian scientists developed the first liquid-in-glass thermometers. These were similar to thermoscopes, but they had sealed glass tubes with calibrated scales marked on them. The scales were usually divided into equal intervals or degrees, based on some fixed reference points. One of the pioneers of this technology was Galileo Galilei, who experimented with different liquids such as water, alcohol and oil. He also invented a device called a thermoscope with balls, which consisted of a glass cylinder filled with water and several glass balls with different densities. The balls would rise or fall in the water depending on their temperature, creating a visual display of temperature changes. Another important figure was Santorio Santore, who is credited with the first mention in print of the liquid-in-glass thermometer in 1612. He used wine as his liquid and marked his scale with 60 degrees between freezing and boiling water. However, there was still no universal agreement on how to define and calibrate temperature scales. Different thermometers used different liquids, reference points and degrees, making it difficult to compare measurements across different instruments and locations. One of the first attempts to create a more consistent and widely accepted temperature scale was made by Gabriel Fahrenheit in 1714. He used mercury as his liquid, which had several advantages over other liquids. It had a high boiling point and a low freezing point, allowing it to measure a wide range of temperatures. It also expanded uniformly and was not affected by pressure or humidity. Fahrenheit based his scale on 3 fixed points: the freezing point of brine, a mixture of ice and salt, which he set at 0 degrees, the freezing point of pure water, which he set at 32 degrees, and the normal human body temperature, which he set at 96 degrees. He later adjusted his scale to make it more precise and convenient, dividing it into 180 equal intervals between 0 and 100 degrees. Fahrenheit's scale became popular in Europe and America, especially among scientists and instrument makers. However, it was not the only scale in use at that time. Another influential scale was developed by Anders Celsius in 1742. He used water as his liquid and divided his scale into 100 equal intervals between freezing and boiling water. However, he initially inverted his scale so that boiling water was at 0 degrees and freezing water was at 100 degrees. This was changed by Carl Linnaeus, a Swedish botanist and zoologist, who reversed his scale to make it more intuitive and consistent with Fahrenheit's scale. Celsius's scale became popular in Europe and elsewhere, especially among scientists and educators. It was also easier to use and convert than Fahrenheit's scale, since it had a simpler relation to water and the decimal system. However, both Fahrenheit's and Celsius's scales had some limitations. They were based on arbitrary reference points that could vary depending on the purity and pressure of water. They also did not have a natural or absolute zero point, where temperature would stop and no more heat could be removed. The quest for finding such a zero point was motivated by some theoretical and experimental discoveries in the 18th and 19th centuries. For example, Robert Boyle, an Irish chemist and physicist, discussed the concept of a primum frigidum, a hypothetical substance that was supremely cold and could make other bodies cold by contact. He rejected this idea as an unwarrantable conceit, but he also wondered if there was a limit to how cold something could get. Another example was John Dalton, an English chemist and physicist, who described a natural zero of temperature that exhibited an absolute privation of heat. He estimated that it occurred at 6,000 degrees below the freezing point of water. He based his calculation on the observation that gases expand or contract uniformly when heated or cooled. This observation led to the development of the gas thermometer, another type of device for measuring temperature. It consisted of a sealed glass tube with a fixed amount of gas inside it. The pressure and volume of the gas would change with temperature, according to a mathematical law known as Charles's law or Gay-Lussac's law. By measuring these changes, one could determine the temperature of the gas. The gas thermometer had some advantages over the liquid in glass thermometer. It was more accurate and reliable, since it was not affected by impurities or evaporation. It also had a wider range of operation, since it could measure very high or very low temperatures. However, the gas thermometer also had some challenges. It was difficult to construct and calibrate, since it required pure gases and precise measurements. It was also sensitive to external influences, such as pressure and radiation. Moreover, it revealed some surprising phenomena that challenged the conventional understanding of temperature. One of these phenomena was discovered by Jacques Charles, a French physicist and balloonist, who noticed that different gases had different rates of expansion or contraction when heated or cooled. He found that if he extrapolated these rates to lower temperatures, they would all converge to a common point at around -273 degrees Celsius. This point was later confirmed by other experiments using different gases and methods. It was called the absolute zero point, because it represented the lowest possible temperature that any substance could reach. At this point, all molecular motion would stop and no more heat could be extracted. The discovery of the absolute zero point led to the creation of a new temperature scale that was independent of any material properties or reference points. This scale was proposed by William Thomson, also known as Lord Kelvin, a Scottish physicist and engineer. He suggested using the same degree size as Celsius's scale, but shifting the zero point to match the absolute zero point. Kelvin's scale became known as the Kelvin scale or the absolute temperature scale. It is widely used in science and engineering today, especially for thermodynamics and low-temperature physics. It is also compatible with other units in the International System of Units, SI. The Kelvin scale has some remarkable features. It has only positive values, since there is no negative temperature below absolute zero. It is also proportional to the average kinetic energy of molecules in a substance, which means that it reflects how fast they are moving. The Kelvin scale is not the only absolute temperature scale that exists. There are other scales that use different degree sizes or zero points based on different physical phenomena or constants. For example, there is the Rankine scale, which uses Fahrenheit's degree size but Kelvin's zero point, or the Planck scale, which uses Planck's constant as its unit and has its zero point at Planck's temperature. However, these scales are not as widely used or accepted as Kelvin's scale. They are mostly used for specific purposes or theoretical considerations. So far we have seen how humans have developed different ways of measuring temperature over time. We have seen how they have used their senses, liquids, gases and other materials to create thermometers and scales. We have also seen how they have discovered new phenomena and concepts related to temperature and heat. One of these concepts was the zeroth law of thermodynamics, which states that if two systems are in thermal equilibrium with a third system, then they are also in thermal equilibrium with each other. This implies that there is a property that is common to all systems in thermal equilibrium, and that property is temperature. Another concept was the first law of thermodynamics, which states that energy can be neither created nor destroyed, but only transformed from one form to another. This implies that heat is a form of energy that can be transferred between systems or converted into other forms of energy. These concepts help to establish temperature as a fundamental and universal quantity in nature, and also to relate it to other physical quantities such as energy, work and entropy. The history of temperature measurement is not over yet. There are still many challenges and opportunities for improving our methods and instruments for measuring temperature. For example, there are still uncertainties and discrepancies in some temperature measurements, especially at very high or very low temperatures. There are also new technologies and applications that require more accurate and reliable temperature measurements, such as nanotechnology, biotechnology, and quantum computing. We hope you enjoyed this episode of An Interesting History. If you did, please like, share and subscribe to our channel for more videos like this. And don't forget to leave your comments and questions below. Thank you for watching and see you next time.